they are completely dedicated to mathematics and engineering and computer science. And now we are starting also the robotics activity of the institute and moving in lab. And we already have some robots and we have also an iPad, but we are also getting a TALOS because now after 8 iPad robots, I really want to have a bigger one.
Sorry to interrupt. Are you not using the microphone
Sorry.
for the record?
Hello? Yeah, sorry, because I'm Italian, so I already speak very loud, so I usually don't need a microphone. Okay. Actually, my motivation for doing teleoperation is because I'm interested in human-humanoid collaboration, and for my research. So my inspiration comes from observing humans, and so if you see two humans collaborating, like in this case, you can see that they are very like natural in collaborating, and their collaboration is smooth. So they're able to constantly predict the intention of the other partner, and they have an exchange of social cues, social signals like gaze and body postural cues, but they also synchronize in with physical signals. So my question is, how can we do something like this with a human and a humanoid robot? And this is something that I would really like to see. And for this reason, I mean, in my lab, we're making we're conducting many different type of researches in this direction. So we're working in the perception of the human, in the exchange of social signals, recognition of the activity and intention of the partner. And of course, we are also working in the humanoid control, because we need to control the humanoid for doing this, and also the level of haptic exchange. But the motivation for teleoperation comes from the fact that somehow I think we need to have demonstration of how a human would want the humanoid to collaborate with another human. And for doing this, my idea is to use teleoperation to provide demonstrations of whole body behaviors. So can we use teleoperation to synthesize collaborative primitives, exploiting the concept of demonstration? And yes, we can, because teleoperation is providing us the equivalent at whole body level of what we have in cobots for kinesthetic teaching. So we cannot do kinesthetic teaching on the humanoid because it's very complex. It may work for like manipulation movements where you can drive the arm of the robot and demonstrate the task. But if the behavior is very complex and it involves like something that is dangerous for its balance, for example, then you cannot do kinesthetic teaching on the robot. So teleoperation is in my point of view, is the way to do this. And so this is, for example, a case where one of our students is demonstrating the ICAP to do like a task. So we have started to work on a control framework to have human-aware physical human-robot interaction, which means that we synthesize the control law of the humanoid, considering also the dynamic model of the human. So with the suit that we have here and also other additional sensors, if we have them, we can have an estimation of the human dynamics. And so we can include this information in the QP controller that is generating the robot movement. And we have shown this in some old papers, but this is like an example of how it works. So we have this student that now he's equipped the XN suit. So here we are taking the kinematic information, and then we are playing this basically in the simulation, and we use this information to as a way to help the robot synthesize appropriate behavior. So we use it to test controllers. But then we want to do this also like online, on live. So this is how our experiments look like. So usually we have the humanoid collaborating, doing something with a human partner. And then we have an operator that is demonstrating how the robot should move. And of course, we have like a ground control operator that is making sure that the robot doesn't go crazy. Like sometimes we can have like sensor failures or something else. So this is like a sort of scheme to say how we do the experiment. Very simply, like this is how the operator doing the motion retarding looks like. So by the way, this is not an engineer, this is a sociologist that was in our lab for a while, and I'm very proud to say this, because if a sociologist can teleoperate our robot, everybody can. Because he really had no idea. Like here now, I mean, he was very stressed about falling because he didn't know that. So we explained that we had a controller that was robust for like failures and wrong retargetings. But he was very stressed. So actually here now, he was our like main operator for a while, so he was like more confident, but believe me, the first time he tried to teleoperate the robot, he was like pale and he was very stressed. But that after a while, he was very comfortable. And this is another kind of experiment. So this is one of my old experiments in Paris, when we were studying like collaborative assembly, something like this. And of course here, the person here doesn't have extensive, she was not equipped with that. But this is the case where you have like an operator, like ground control operator that is monitoring the robot status. So it's hidden. The subject here doesn't see that. Okay. So I want to tell you 3 things that we are working on right now to improve the teleoperation experiments. So first is how we do the teleoperation to have like a sort of robust teleoperation, how we call, which means that if the human is doing a movement that for the human is okay, but it's not okay for the robot stability, then we kind of filter this kind of movement. So we make sure that the robot doesn't fall, even if the human, like for example, falls or do something like that could prevent the robot status. And this is what you already showed before. And then sometimes in teleoperation, the operator may do something that is off the script. So we don't know in advance what the operator is going to do. He may do some crazy movement that we don't know about. He may sneeze, okay? So this happened, by the way. Or maybe there is a guy that is passing and he say, hey, and this was like off script. And we need to make sure that we have a controller for the robot that is able to do also the unexpected movements. So we cannot have the controller that is only capable of doing the sequence of movements that we know are needed for the task. So we need to have a way to parameterize, to auto-tune the controller, to find the optimal parameters so that we know that the controller is able to do all these kind of movements. And then the third point is that even if we teleoperate the robot and we are able to retarget the motions because we want to synthesize collaborative behaviors, we don't know if these behaviors are really optimal for the robot, because the human body is different from the robot body, and even for robots like ICAP that have a high level of anthropomorphism, the dynamics of the two is different. So a movement that makes totally sense for a human, yeah, maybe on the human it works, like visually you can say, oh, it's very nice, it's like human-like, but it's not really optimal for the robot. And actually this is something that we observed. Some movements that we were doing, for example, lifting weights, etc., they were kind of almost saturating the joint torques of the legs of our robot. So we said, okay, we have to find a way to demonstrate collaborative behaviors, but to optimize these motions so they are like more adapted for our robots. So I'm gonna try to do quick because I'm afraid that it will take too much. So this is how we do the teleoperation. So this is what I already showed. So we have our operator that is like moving, and we have a simple mapping. Actually, we are experimenting 2 kinds of mapping, like Cartesian maps in some key frames, like end effectors and whatever. And we are also retargeting joints, as Kurush was demonstrating before. And what we are very interested in is this capability of detecting like instabilities, so movements that are dangerous for the robot's stability, and so we don't execute these motions. And it's not even falling. Sometimes in the case of the ICAP, you can really do something that for you it's normal, but it may make the ICAP fall. So this is how we do it. So we have a first part where we do the retargeting, and then we have this, we call it dynamic stabilizer. It's basically a ZMP correction that avoids the robot to fall. And then we have a whole body QP controller with multiple tasks. And this is something that I will see how we optimize this later. So by the way, we also try to do the retargeting footstep. So we try to combine our framework with a single footstep retargeting. our results were really not convincing. We really don't like the way it behaved, because even if Augusto, our operator, was walking very slowly, it's not possible with the ICAP. I mean, it gives us something that is completely unrealistic. And also we were interested in retargeting footsteps to avoid obstacle, like to jump over obstacle, but at the end with ICAP that doesn't really work. So we abandoned this line, and now we are doing, I don't know why it's not, okay, so for the walking, we are just coupling our whole body retargeting, which is more for double support and manipulation, with the retargeting, so with the, sort of upper body retargeting coupled with the autonomous walking pattern generator that is just making the robot walk. This doesn't solve the problem of obstacle avoidance in case you have to step over an obstacle, but we're working on a solution for that. And this is something like how it works. So we have we use like the joysticks of the Oculus system to just command the robot to move forward and turn in case. And we have like a footstep planner with the MPC controller for having handling the walking. It's something like very basic and state of the art. It's not, but it works. Okay. So now the first problem that we had when we wanted to solve is that sometimes, so when we have our robot, when we have our controller, we want to make sure that we are able to do, with the same parameterization of the controller, many different motions, not only the motions that you use for tuning the controller, which is an operation that often is doing by hand or by an expert. So we have been working for many years in auto-tuning the QP controllers, like learning on optimizing soft weight, strict task priorities, soft task priorities, and also trajectories in the tasks. So right now, for in auto-tuning the QP controller for teleoperation, we have basically this framework where we acquire a data set of many different possible motions that the robot could do, not only the motions that are of the task that it has to solve, like the mission, but also movements that are like random, like dancing or whatever. And we have our data set. We take the recorded sequence, we execute them, and then we compute on every rollout of the sequence some fitness scores, like robustness scores that tell us if the motion is robust to perportation, tracking errors, so how much loyal we are in tracking the desired demonstrating behaviors, and we compute like sort of false score in case the sequence is not, so the sequences cannot be executed with this parameterization. And then we use these fitness scores, we send them to a multi-objective optimization algorithms that tries to find the best parameters that optimize the three fitness scores. And then from this multi-objective optimization, we can select the best set of parameters by looking at the best solution on the Pareto front. Okay, so it's going to, it doesn't. So this is how we do. So first we record these movements. We use the retargeting framework. And then basically this entire process of optimization goes online. It's offline and it's simulated. It's not directly on the robot. But for a good reason, because given the number of evaluations, it's not feasible to do it online on the robot so far with this technique. We are working also on making it possible to do it online in few trials, but it's a different story. So for doing this, so to basically find automatically the best configuration for the controller, what we do is that we define a general stack of tasks where we have different levels. So we have different priority levels, and we also have soft-weighted combination of tasks in each level. And then we take all the parameters. So basically, in each level of the stack, we have the combination of all the possible stack with the weights. And then we optimize for this parameter. And then to optimize for the level of priority for each task, we use what we call task selectors. It's like a parameters that you tune, that it can say on which level the task goes. And so we have all these parameters, and then we put them in our machinery. Okay, I'm stop using this, and we'll use this. So we optimize for many different tasks, torso, arms, foot pose, whatever, waist, comb, etc. We have the entire control parameters, which is a list, and then here you have the multi-objective optimization framework. I don't know if you're familiar with, we use NSGA2, which is one of the most known multi-objective algorithms for evolutionary computation. And then when we solve our problems, we have all the solutions on the Pareto front, and so we can choose the solutions there. And you can even take the solution, so you can test many different solutions by looking at the Pareto front, and you can decide if you want to promote more, for example, the robustness or the tracking error, etc. So this allows you to choose between different controllers. This is results of what we obtained as controllers for many different sequences. So we obtained different values and intervals for the parameters, for the priority weights and conversion gains, and also for the task selectors. And the task selector is what is really interesting because so this was computed on many different executions, many different trials. And so from this, we have like an indication of where to automatically put the structure, so how to automatically choose the structure of the task. Like for example, for the sequence that we tried, the feet goes in the top priority with the head the task, it was the head orientation, then medium priority, the end, the comb, and so on. So I know that many people in the humanoid community say that the tasks are fixed, like the structure of a QP task can be fixed. But in our experience, often we have to tune depending on what we do or what the robot is doing. If it's doing something that involves like balancing or fine manipulation, usually the controller is different, and our students have to tune the parameters. So we don't tune anymore. We just auto-tune with this. Okay, and this is what it looks like at the end of the process. So we can, in this case, we found that for double support motion, we can simply transfer the solutions to the robot. Why? Because also like we had noise in the optimization process, so we can also find for parameters that are robust to perturbations. Okay, and it works on the robot. And the nice thing that it works, so it does not only allow us to execute motions that are part of the training set, but we can also execute for other type of motion, and we can use it online for teleoperation. So this is like one of our controllers that was optimized, and here the robot is teleoperated, so the operator is not very good in teleoperating, you can see. No, I'm kidding. And here, it lost a piece of the finger, but it's not a serious damage. So here the operator is still operating the iCap for doing many tasks in a different way. So it's like opening the door, and then we have lifting weights. I mean, I will try to see if I can go here. Okay. So here is lifting the box. The box is not very heavy, but iCap cannot lift more than half a kilo anyway, because then it would saturate the shoulder joint. So, but I mean, it allows us to experiment with many different motions, like doing more of this and then throw the boxes. And this is completely unscripted. So it's the operator is deciding what to do. Yeah, and okay, my student likes to dance, so he made the robot dance. Okay, so the last piece of thing we are doing for optimizing the teleoperation is to optimize for demonstrated movements. So as I said, I want to use the teleoperation for demonstrating possible collaborative policies to the robot. So how the robot should move when he's interacting with the humans. And the problem is that when we demonstrate the movement may be optimal from the point of view of the human. The human could say, yeah, this is the movement that I would like to do, but it's not optimal for the robot body. And so what we are doing is that we are recording retargeted trajectories, and then we have an optimization loop where basically we re-optimize these trajectories for the robot dynamics. So basically, the framework consists of two main steps. We have an offline step where we record several demonstrations of the task made by the human. This is also interesting because we're able to account for the variability of the robot, variability of human demonstration, which is something that is normal. Every demonstration we do is different. And then we have like a probabilistic description of the demonstrated behaviors. So we retarget this behavior, we generate for the robot, and then we have an offline optimization loop where we optimize for the robot. So this is in the first part. The student makes several demonstrations, and then we use probabilistic movement primitives to synthesize this trajectory. It's our choice. Actually, we do it because then we would like to do the prediction over these demonstrated trajectories to have generate anticipatory behaviors. But it's a choice. Any primitive or other method for approximating parameterized function would be okay. And then the second part is an offline optimization loop where we optimize for the parameterized trajectories, so that we can have demonstrations that fit more the robot bodies. We tried for this. We tried several algorithms for optimizing parameters. So the problem, the structure of the problem is that we don't have the gradient in our optimization problem, so we cannot use gradient methods. So we are using black box optimization algorithm. We are comparing several, like global and local, like AGS, cobildance, CMIS. And at the end, because we think CMIS is the one that we like most. It's again an evolutionary algorithm. It's a constrained stochastic optimization algorithm. The reason we have it constrained is that we have to make sure that the optimization problem generates trajectories that are always feasible and that they satisfy the system constraints, like the robot constraints. So that's why we look for a constrained optimization. And that this is how it looks like. First, we have an initial demonstration that is the one provided by the human, and then we optimize the robot for a given fitness. So in this case, it's our job to define the fitness. Like we want to have motions that are like faster or slower, or that that reduce the torque consumption, for example, or they are more conservative from the point of view of the ZMP or whatever. So of course, if you change the type of fitness, you will attain different trajectories, optimized trajectories, but this is the way, it's our choice. And at the end, the optimized solution also worked on the robot. In this case, it's not very human-like in this demonstration, but it's normal because our student chose to optimize for specific joint torques. And these are the joint torques that we usually saturate when we do whole body movements. Okay, so this is like basically the conclusion of what we're doing. So the main things we're doing in teleoperation. So besides classical like teleoperation for local manipulation with the ICAB, our main thing is to automatize the process, so to use optimization techniques to auto-tune the controller for teleoperation, and also to improve the trajectories to make them like more suitable for the robot. So we can use them for demonstrating collaborative strategies. And for the third task, you can see our student, Waldes Gomez, is giving a presentation tomorrow in the oral session of optimization, so you can ask him more questions about that. Thank you very much. These are the 3 students, so the work I presented was done with these, our students. And so thank you very much. I don't know if you have questions. Yes? So the optimization of the trajectories over the parameters. So the trajectory is just for generating collaborative policies. And these collaborative policies are evoked online in the moment that you do because I don't have so imagine the QP controller. So you know you have tasks like X minus X desired. So this X desired can come from a collaborative policies that you pre-optimized offline. So for the moment it's offline. It takes like the entire optimization takes less than 1 hour in a standard laptop doing other things. On our cluster, it takes a few minutes. It's still not enough for doing, but it's something that it's just a prior knowledge that you have, and you can optimize offline if it's a prior. Yes? Yes? So in the way we optimize, the task can be only, so we have a task selector. So at the end, when you optimize, the task can be only in one level of the, we don't swap the task. Once we find a good configuration that works for all the task sequences, the demonstrating sequences, then this is the configuration. So it's a bit of, so in some frameworks, you have the QP structure that changes over time depending on what you do. And in this case, it's different. Maybe we lose a bit in terms of performance because we don't have specialized controller configuration for special tasks, but we have like a global sort of generic control configuration that works for everything. But it's true that this is like not depending on what you do, like for fine manipulation tasks, like if you have, like you are standing and you do some screwing, something very precise. In that case, maybe it's better to use a very precise controller configuration that is optimized for this specific task where you really need to have high performance, for example. So we do this for this week exactly, and we are coupling this with an activity estimator. So we estimate the activity from the human, and then we say, okay, in this case it's this activity, so it's this controller. But in this case, we really like to have a generic controller if you don't know what the operator is going to do. Okay. So maybe we can switch to the next presentation. Actually, the next presentation is like a video. It's like if we were at the movies, because so we had invited Nakanishi from Gitai. Where is my? So you see Yuto Nakanishi, and they couldn't come, so they sent a video. So this is kind of weird, but I saw the video yesterday. It's not bad. So if you think it's boring, I can skip some parts, because in some part there is no audio, so it's a bit heavy. But in the first part, the presentation is not bad. So the problem is that we cannot ask questions. Wait.